And it may be period 4, but you're actually going to investigate period 3 oxides. And so first thing we'll do is just look at which ones they are in the periodic table. So we've got an N equals 3. And to begin with, we're going to look at the elements, just to familiarise yourselves with each of the elements of period 3. So you're just going to pause this and fill out the table, obviously on separate paper. And then we will go on to which are metals and non-metals. So got a outline of the periodic table here with the step between metals and non-metals, and have scooted hydrogen across to reinforce that it's a metal. It's a non-metal on our planet. And looking at the metals and non-metals and asking why silicon is different. And you can just pause and answer that one. So, looking at each of the elements, we're looking at in particular at the oxides of them. And so the first thing you have to do is to write the formulas, because we're going to look at the properties of each of the oxides and try and understand why they have the properties that they do. So pause here to write the formulas of each of the oxides. And that's just a summary. And then going to look at, again, each of the period 3 oxides and identify which bonding type is in each. So just look at them, make a list, and write down what you think. So pause again to complete that little mini activity 5. And so I'm going to show you the structures, different ways of drawing each of the oxides. But I don't want you to learn the structures, but just notice the differences as you're looking at them, and relate that to the bonding types each time. And I ask you to identify the oxygen atoms and which period 3 element you're dealing with. So here we have sodium, and we've just got a unit cell with a number of sodium ions in it, with the associated oxygen atoms as well. And pause to look at them more closely as you're going through. We've got magnesium oxide here. You can identify the magnesium and the oxygen ions, hopefully by their relative size as well, from what we've been studying about ionic radii. And here we have interesting structure for aluminum oxide, and again to identify the aluminum atoms and the oxygen atoms as they're there as well. And then we go on to silicon dioxide, a giant covalent, and you're just getting a sort of single unit cell look at them. And then we've got a molecule, nothing giant, no lattice, and we've got diphosphorus, sorry, that should be tetraphosphorus digoxide, or diphosphorus pentoxide, it's sometimes given, dividing it by 2. And here we have tetraphosphorus hexoxide. So there are 2 different structures that you can have for the oxide of phosphorus. A molecule as well, and that's going to be covalently bonded. And then looking at sulfur dioxide, and if you're comparing it perhaps to water, and thinking about the basic tetrahedral structure with lone pairs of electrons, you've got different electronegativities which are determining the the polarity of those bonds there, and not showing the lone pairs of electrons. And the same goes with sulfur trioxide, a molecular structure. Then we go on to chlorine and dichlorine monoxide, and again compare that to water, but you've got electronegative chlorine atoms which alter that central bond angle. And then dichlorine heptoxide, again covalent, and of course argon isn't going to form an oxide, and we're not looking at its structure. Number 6 is interesting because it then allows you to look at differences where you have more than one oxide, as we saw 2 structures for the same period 3 element, and we're going to work out oxidation state. So read through this, then pause it to work out where the question marks are. So you'll be doing this officially in Unit 9, so about a year from now, but it's a good idea just to foreshadow what's happening. So if we look at the first one, P4O6, you need to know the oxidation state of oxygen is -2, so you're given that information, and the sign, minus sign, comes before the numeral. So we're not here totally, we're not dealing with an ion, because phosphorus oxides are covalently bonded anyway. So -2, and the sum of all oxidation states in the molecule, or indeed a formula unit if it's ionic, is going to be 0. So those are the 2 rules you're going to apply here. So for P4O6, the sum equals 0. So 4 times X, which is the oxidation state of phosphorus, plus 6 times -2, where you've got 6 oxygen atoms with oxidation states of -2, the sum of all of that equals 0. So do the algebra, and it comes out to +3. And you can pause and do it for the other elements that are here. Looking at electrical conductivity, very much related to the bonding that is present between them. So you have to look at those, and I'll give you a little hint that no solid is going to conduct electricity, well, bolts of lightning, but small manageable currents won't conduct. So you'd have to melt them, and that's what you do. Which ones will conduct electricity when molten? And so pause to consider that and put your answers down for later. So looking at the pH of period 3 oxides, in order to measure with indicator paper or indeed a pH probe, you have to have a solution. So again, that's what we would be dealing with, solutions of each of these, and predict what their pH will be. So pause and wait. So whilst you've predicted, write 3 equations here for the metal oxides reacting with water, and what are their products. So what names do they have, and what do you expect the pH of those products to be, to confirm what you've already written. And for sodium oxide, magnesium oxide, aluminum oxide, and number 10, write equations for those metal oxides reacting with nitric acid. So again, another pause here to work through it. And then we go on to some non-metal oxides. So start off with I've got here sulfur trioxide in water, sulfur dioxide in water, and what are those products. So pause and do that one. And then try these ones. Using the pattern that you've had for for sulfur dioxide, sulfur trioxide, look at the ones that are here and see what you come up with. Try them. It's not to look it up just yet, but try them. So pause before you go on. And here we have silicon dioxide reacting with an alkali. So we're making a silicate ion. And really quite interestingly about aluminum, or aluminum oxide. Now it is special. Why? Because it's a metal oxide and it reacts forming aluminum hydroxide, and metal oxide reacts with acids, but it also unusually reacts with bases. So there are only 3 of the elements that do this. Only one of them is in period 3 though. The other 2 are zinc and lead. So here we will have aluminum oxide being able to react with acids because it forms aluminum hydroxide, and also being able to react with bases. And it's called amphoteric because it reacts with both, the amphi bit as amphibians, land, water, etc. Next bit, a summary. So just pause to look at what has been written here. And really there are some answers to previous questions, and you might want to just look at the answers that you've put and check on them. And remember in our next class to ask questions about anything that you want to. So pause while you do that. And here looks really quite like a similar one as well, but going through the applications of and skills, which is looking as well. It's asking about oxides of nitrogen and sulfur with water. We've dealt with sulfur, but what do you think would nitrogen do? And so a few questions here. So pause and work through those ones. They're reinforcing what you've already just been looking at. And if you've got any doubts with any, bring them to our next class. And so some more ones, only if you have time in our async classes. So if you're pushed for time, this isn't a homework activity from the async classes, but if you do have time. And then the next slides really just go on through the IB items, and they've got some answers here, but they're relating to period 3 oxide, so specifically. And here we've got acid deposition, which you'll look at in detail, in particular with Unit 8, acids and bases. There's a really good environmental application section on that. And then some theory of knowledge. So pause and just read through that and ponder on it for more than a minute or two. And really a summary of what we've been looking at with periodicity as well. And with the oxides, it's taking it further. And then following on from this, just a couple of other slides, which is going to be the stable structure for sulfur trioxide. This has the lone pairs, so a complete Lewis diagram here. And see if you can remember that. And then giving the formulas which we've been using subsequently from asking you that question, but check your formulas. Looking at the bonding types, so these are responses, answers that help you. And then the oxidation states here, and then the conductivity to check your answers, the pHs, and some of the equations that are here. Particularly with the non-metal oxides forming somewhat chunky looking acids, some of which you're familiar with and some of which are new. And that will bring us back to where we were. Okay, so I hope you know, I don't want to say more about period 3 oxides than you want to. That's not quite right, because you've gone into the chemistry and it's the trends that are important, because you can apply it to other periods. The IB specifically will ask about the period 3 properties. Okay, thanks for all of your hard work.